Hello everyone, welcome back to the another video in the series of YouTube academic projects that has been started by Spartificial. I am Rohan, and in this video I will take you along with me on this journey of predicting the number of sunspots. And now this is the basic workflow that we'll be following throughout this video, where we will start by first setting our base on the ideas of sunspots, then move on towards the actual data set, understand it properly, and then look into the problem statement. That is to build the model to train it to learn the pattern of the number of sunspots observed in previous years. And then based on this learning, we'll make our model do some predictions on how many sunspots we'll be able to see in the future years. Now, before we dig into this project, if you are new to the concept of YouTube academic project series that we have started, then let me tell you that in each video, we'll bring some cool project like this, where we'll get you started with this project and teach you the major concepts being used over here. And then we'll also leave some tasks for you to solve in each video. Now, based on the submissions of this task done by you, you have this opportunity to get certified for the hard work and time you will spend on completing this task. And feel free to add it to your resume, and it shall surely help you in order to showcase your skills that you have achieved by solving these tasks. So now, are you excited to get started with this project? Well, do show us some support by liking this video if you learned something from it. Also, share it ahead with your friends and do not forget to subscribe our channel for more such content in the future. It will help us keep us motivated with your love and constant support in order to bring such videos for you. So without any further ado, let's get started with this project. So one interesting aspect of the sun is its sunspots. Sunspots are areas where the magnetic field is about 2500 times stronger than that of Earth's, much higher than anywhere else on the sun itself. Now, because of the strong magnetic field, the magnetic pressure there increases while the surrounding atmospheric pressure will decrease. This in turn lowers the temperature relative to its surroundings because the concentrated magnetic field inhibits the flow of the hot new gas from the sun's interior to its surface. Now, sunspots tend to occur in pairs that have magnetic fields pointing in the opposite directions. A typical spot consists of a darker region called the umbra, surrounded by the lighter region known as the penumbra. Now, the sunspots appear relatively darker because the surrounding surface of the sun, also known as the photosphere, is about 10,000 degrees of Fahrenheit, as compared to the umbra is only about 6,300 degrees Fahrenheit. Along with that, sunspots are also quite large, as an average size is about that same of the Earth. Also, sunspot increases and decreases, then again increases and decreases through an average cycle of 11 years. Solar cycle 1 was first solar cycle since the extensive recording of the solar sunspots actively began in 1755, and we have experienced a total of 24 full solar cycles since then. Currently, we are in 25th solar cycle, the solar cycle 25. It began in 2019 December and is expected to last for more approximately about 11 years, and that is about 2030. So yeah, that is pretty much about the information that we need to have in order to get started with the data set. So now, just in case if you are interested into learning more about the sunspots, you can go ahead and click on this link, or else you can also try one experiment to observe the sunspots directly with the help of binoculars. But now there is one condition: you cannot directly see the sun with the help of the binoculars. It's going to damage your eyes. So there are certain steps that you need to follow in order to project the sun with the help of binoculars onto a particular white screen. And then, depending on the amount of binocular that you are having, or maybe the telescope obviously will be giving you a better version of it. But let's say that if you're only having a binocular, it's still going to give you good results, because I've personally tried it and it has been working out pretty much good. So that's why I thought to share it with you guys, that you just go through this both of these videos. It will help you understand how to have a setup with the help of a binocular, that you can project the sun on a screen and you will be able to visualize this kind of sunspots. And is also pretty much useful in order to look at the transit of the Venus when it passes in between Earth and the sun. So again, that is one more cool thing that you can do with the help of the same idea that has been explained over here. So please go through it if you are interested for this kind of experiments. It is pretty much really very exciting to do it as a beginner in the field of astronomy. And now that because we are ready with the knowledge that we need to understand the data set for this project, let us go ahead and look into its content. So for that, I'll click on this link. It will take me to this Kaggle web page. And over here, we can find all the information regarding this data. We are having the context, where we are talking about the basics of sunspots and the 11-year solar cycle that we have just discussed about. And then inside the content, it consists of only one file, and that is sunspots.csv file. And Within that, there are three different columns, where the last column is the one that is going to be the part of our interest, which contains the monthly mean total sunspot numbers observed from 1749 to 2017. Now, just one thing to note over here is that this 2017 will just depend on what is the last update that this CSV file is going to receive. So currently it is 2022, so we can expect there a different date at the end of the data set. So we'll look into it, what is the last date that we are having for our data, with the help of pandas. So while doing the whole analysis process, we'll be using pandas. So over there, I'll be showing you what's the last update that we have received for the CSV file. And then the second column is nothing but, see, now this is because this is the on an average, what is the total number of sunspots we have seen on that particular month. Now, when we are recording this value, we are recording this value on the last date of each and every month. So starting from 1749 year, we are looking at the 31st January. What was the total number of average number of sunspots that we have observed throughout the month of January in 1749 is what we are seeing over here. And that's how we are just going to add the data over here of the monthly mean total number of sunspots on the last date of each month, starting from 1749 to whatever is the last year. So that's the kind of data set that we are having. And now we can simply go ahead and add this dataset to our Kaggle notebook. In order to do that, I'll click on this link, copy it, close this window, come back to our Kaggle notebook, click on this arrow and then click on add data. And over here, you are just going to look for this URL. And then it's going to give us the same dataset that we just looked into. And then click on this plus sign to add it to our notebook. And then within few seconds, we'll see that it has been added. Let's just cross it. So we can see that as in part of the input of this notebook, we are having the sunspot data ready to use. And if I click on it, we are having the sunspot.csv file. And yes, we are now ready to get started with our project. So let us now start with the coding part. First of all, I'll be importing all the necessary libraries that we are going to use throughout this project. Starting with the visualization ones, I'm importing matplotlib and seaborn. Then in order to handle the CSV data that we are having and to deal with the arrays in linear algebra, I'm going to import pandas and numpy respectively. Then in order to manipulate the data that we are going to look into throughout this project in a way that our model is going to understand, and then to build the model, train it, test it, and all that kind of stuff, it's going to be taken care with the help of the TensorFlow. So I'm also importing that. And then to avoid any kind of warnings that I'll be getting throughout the coding cells, I'm just using these two lines of code, that is importing warnings and then warnings.filter warnings. I'm simply going to ignore all of them. So this is the basic stuff that you must have seen in all the other videos that we have uploaded in this playlist. So yeah, that's pretty much about importing the necessary libraries. Now let us take a look into the data that we are having. So I'm creating this data is equals to, I'm just creating the pandas data frame with the help of read_csv file, because we are having this CSV file over here. So in order to read it, what I'm going to do is I'm going to copy this path, close this, and just paste that link over here. And then I'm going to say that data.head, and this is going to give me the first 5 data points inside that CSV file. So it consists of, this is the by default index that we are having of pandas. So you can just keep it. This is the first column, this is the second column, and this is the third column. So in the first column, we are having the index. Then in the second column, we are having the date in the format of year, month, and day. So this is the 31st of January 1749. Now, because we know that the data that we are having is nothing but on the last day of the month, what is the average mean total sunspot numbers that has been recorded throughout the month? That's the number that has been written over here. So starting from the 1749, we know that the data was starting from 1749. But what is the date at which we are going to end this record? So for that, what I'm using is data.tail. So it's going to give me the last 5 data points of this whole CSV file. So using data.tail over here, I'm going to get this last five data points. So over here, we can see that 3264 is giving me the value of date as 2021 January 31. So starting from 1749, we are having the data till 2021. So as I mentioned earlier, that the dates will just keep on changing depending on when you are using this data set. So just don't worry if you are seeing some different dates. The overall process is just going to remain same. So now let us just go ahead and look into the general information that we are having of this data with the help of .info. So you are using this data, the data frame that we created, and then .info is going to give me all the kind of information. And by looking at this, what we can figure out is there are a total of 3265 data points, because we already know that the pandas data frame starts with the index of 0. So 3264 over here just gave a hint that, okay, there are total of 3265 data points. And then there are no any kind of null values present in this data. That's pretty much fantastic. And now the data type. The data type of this index is given to us in the format of integers. The dates are given in terms of object, and the monthly total number of sunspots are given in terms of float. So mainly we are going to use this data. So it is already in the numeric format, so we don't really need to convert. And depending on the memory that you are having, you can convert these values to float 32 or float 16, whatever is suitable for your system. But float 64 is going to work for my system, so I'm going to continue with the same without doing any kind of manipulations with this data type. And now let us just go ahead and extract the values of the sunspots, or I should say monthly mean total sunspot numbers from this data frame. And in order to do that, what I'm doing is I'm creating a variable called sunspots. And then I'm saying that from the data frame, I want to extract the locations. I'm extracting all the rows from the last column. Remember that the -1 is referred for the last column or last value in a particular list or anything in Python. So that's why I'm using -1 over here. And using that sunspot.values is going to convert that data into the numpy array. So here is the data frame or the numpy array that I got by converting the data frame into that particular format. So you can see that the number starting from 96.7 and all the way down till 10.4. So that's what you can also see over here, starting with 96.7 and ending it with 10.4. So this is just the sunspot numbers that we have just extracted from this data. Then let us just visualize this data. For that, I'm just going to start by giving the size of the figure. I am just using 28,6. You can just change this depending on the way that you want to visualize your data. Then I'm simply going ahead and plotting this sunspot numbers. So because I'm just giving one argument, it automatically means that all the other values over here are starting regularly from 0, 1, 2, all the way up till the last data point that we are having. So because I know that the index are just the regular ones starting from 0, 1, 2, 3, 4 and all the way down till 3, 2, 6, 4, I'm not changing any kind of these things and just saying that, okay, yeah, my plot is going to contain all the values in between 0 to 3265 or 0 to 3264. That's what I should say. And for the respective values, I'm simply going to plot the y as the sunspot values that I have extracted from the data frame. And then just giving the y label. And in order to get the y label, what I'm doing is I'm using data.columns of the last column, right? So data.columns is going to give me the list of all the columns that we are having, and -1 is going to just extract the last value or the last name of the column, that is the monthly mean total sunspot number. And that's what we can see over here. And then for the X label, I am just giving it the name from that months from Jan 1749 to Jan 2021. So that's the X axis, and then giving the title and then just showing this whole diagram. And we can see that this kind of pattern is observed over here. Now, few things to remember. The first solar cycle started from 1755, but our sunspot data started from 1749. So that's a total of 6 years of gap. So if you just subtract these two numbers, I'll be getting the value of 6. Now converting into months, I'm simply going to multiply that 6 with 12. That is the total of 72 months of data. Now, why did I convert this years to months? Because if we look into this data, we can see that all these data points are in terms of months. That's for January, February, March, April for the 1749 year. We are having this data in terms of months. And that's the main reason why I converted this 6 years into the months. So if you look into the graph, the first part over here, this first part, that the part that is decreasing till the minimum over here, is nothing but with respect to that months of data where the solar cycle didn't even start, because we know that in the solar cycle the pattern that we see is generally usually like this, right? So that's the exact reason that I'm highlighting this point over here. And then we know that approximately each solar cycle lasts for 11 years. So converting into months, it becomes 132 months of data. So all these minimum points are approximately 132 months away. Some may be even more, some may be even less, but the approximately on average we are talking about is this all data points are 132 points away from each other. And now the current cycle that we are having right now is solar cycle 25. It began in December 2019, but the end data that we are having in this data set is still January 2021. And that's the reason why we are seeing this extra hump going upwards. And now that's about, because if you look at the difference between the December 2019 and the January 2021, that's roughly about 13 months. And now for that to highlight over here, what I'm going to do is I'm just going to create one more coding cell. And over here, I'm creating this figure again, and then plotting the sunspot data, the blue part that we can see, the normal data. And then on that, I'm just highlighting the points that I've just mentioned above. So the first 72 months of data is just for the 1749 till 1755. And then from that 1755, I'm just going to add 132 months. So that's why I'm saying that now, for in order to highlight this green part, the first solar cycle, it's going to start from the month 72 approximately. Okay, it's not exactly 72, but yeah, approximately 72. So starting from the 72 month till 72 plus 132, I'm adding extra 11 years from that 72 point. And hence I'm saying that starting from the 72th month till 72 plus 132th month, I'm going to get my first solar cycle. And that's what I'm highlighting in the green. And then, as I mentioned, the approximately last 13 months is contributing to the current solar cycle that just began in December 2019. I'm just showing it with the red part. And for the respective coding is been done over here. And usual stuff apart from that is the X label, Y label, and the title, and just the legend that we can see over here. I am using this line of code and simply showing this curve. So that's about highlighting this point that I just talked about. And now, in order to visualize the solar cycle properly in terms of years, I'm again going to do some extra coding so that it's properly visualized in a way that we are used to, the way that we saw in the earlier part of this video. So for that, what I'm doing is, if you can see, the final output that we are having is, this is the first solar cycle. This is second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So what I'm doing is, I'm just taking the first solar cycle till 24th solar cycle. I'm just cutting all the part for the, the first, that there was not even part of the solar cycle, and the current solar cycle. I've just omitted that part just for this visualization purpose over here, so that we are able to see it. And we can see that the data is exactly fitted over here. Few of the data points we can see somewhat there is a mismatch, because as we mentioned, it's an approximately 11 years, not exactly 11 years. That's why we can see there's a bit of a mismatch of the years over here. But again, it started fitting it properly over here at the end of this 24th cycle. We can see that again we are getting approximately 11 years of cycle. So that's all about the visualization. But how have I done it? What I'm doing over here is, I'm just starting by creating an empty list for years and creating the starting point. And then I'm using my for loop, and I'm saying that for I in the range of starting from the 0 point, and then I'm taking the length of the data from the location. So this is nothing but this sunspot data. Okay, if we want, we can directly use the sunspots, because that's nothing but exactly the sunspots that we had extracted. It's just that in order to code it very quickly, I've just used the same thing. And then what I'm doing over here is, I'm taking the data points from 72, because I know that this is the starting point. So from that 72 point, I'm considering all the data, and then I'm just skipping 132 months of data, and whatever is the value, I'm just appending it, and then just adding 11 to the starting value, because I know that all these years are 11 years apart. So in order to get these labels, I'm just adding 11, 11, 11 to get this kind of values all the way till 2019. And after that, I am simply just adjusting my limits of x-axis, giving my x ticks starting from 1755, or what I'm actually doing over here with the x ticks is, I'm highlighting these points where I want to label, and then just converting that values, this values will be nothing but this kind of values that we are having over here. I'm first of all highlighting these values and then converting them with the years, because we know that in the years, the data that has been stored is of 1755 till 2019. So that's what I'm doing with the help of plt.gca set xtick labels. What was the previous values that we are having over here? I highlighted them and simply replacing it with the years that we just created over here, starting from 1755 till 2019. And let us now just draw some extra conclusions that we can see from this graph. This graph is pretty much noisy, if we can see, and it contains some crazy, insane values like about 400, whereas the maximum sunspots ever recorded in a particular solar cycle was 285, and it was done in the solar cycle 19, that is in March 1958. So we can see that around that value it's not anywhere closer, so it must be some kind of error while measuring this particular value. So this is just kind of the data that we are having currently. And now this kind of sequence of data points indexed in terms of time is simply referred as the time series data. So what we are dealing with right now is called time series data. So now there are few tasks that is associated with the plots that we have plotted over here with the help of Seaborn library. Again, I'm giving some kind of figure size for the visualization purpose. Giving the subplot starting with the 211, this is going to give me the 2 rows and 1 column. And in the first place, I want to create the disk plot of sunspots. And then in the second index, I want to create the box plot of the sunspots, where sunspots is nothing but the time series data that we were having. So whatever conclusions that you see over here and what kind of things you can do with help of this box plot and this disk plot is what is one of the part of your task. If you just look into it, you can see that there is somewhere I have mentioned about the, yes, write down your conclusions from the disk plot and the box plot that we have made earlier in this notebook, and then you can treat this outliers and see if any kind of performance is improving or is it not improving, whatever is the conclusion you just mentioned about it. So that's your task that you have to do with help of these plots. And now we are having the sequence models for the time series data. Now, because currently we are dealing with the time series data, we want our models to remember some information from the past in order to retain the patterns of the sequence of the data that we are having. So if we can see that there is a certain kind of sequence or the pattern of the sequence that has been repeated, so we want our model to learn this kind of pattern. So for that, our model needs to retain this kind of information from the past, and the traditional neural networks, the artificial neural networks, are not capable of doing that. So for that, we are having this unique kind of architecture which we refer to as recurrent neural networks, and there are different variants of the RNN. We'll be talking about it in a while. But what is a basic version of the recurrent neural network? That is what we can see inside this image. So how is it different from the traditional neural networks? So instead of having multiple dense layers over there, over here we are just having one unit. It consists of one dense layer, but now one unique thing about it over here is that it takes in inputs in a different time. It goes through the time. And that's why over here it's not back propagation. Now in RNN, we are having back propagation through time, because for each and every time step, we are going to feed in some different inputs. It's going to also give out respective outputs. And now that outputs are again fed in with the new inputs for the new time step that we are going to give. So if you're confused about what is actually going on, so let us just unfold this RNN. So if we will unfold this RNN, this is how it's going to look like. So this is the current time step, this is the previous time step, and this is the next time step. So this is what we are actually doing. So see, what's the basic idea? We are taking the output from the previous time step, and this same output is what we are feeding over here along with the new input of that respective time step. So both of them together is going to compute a new output for the current time step. And now because we are feeding the output from the previous time step, we are able to retain information from the past. And now again, for the new time step, again we are going to take this output from the previous cell, because now this output is also containing the output from the last cell. So all these kind of outputs that we'll be using will have the information of the past. So if we feed in this output to the next time step along with the new input of that time step, again we can compute this new output. So all of this are not different dense layers. Okay, this is just one unit of RNN which is just repeated over and over again. It's not different kind of dense layers that we are having just like traditional neural networks. It's completely different. Over here we are having hidden weights. So these weights are constant and shared throughout the time step. This will never change. And now also for the inputs, all the kind of inputs are also going to have same kind of weights throughout each and every unit. And again for the output we are having different weights. Now this weights again will never change for the output. So this input weights are denoted by U, this hidden weights are denoted by V, and this output weights uh, are denoted by W. This U, V, W will never change throughout the single unit of RNN. Now, as I mentioned, there are different variants of RNN. What we can see right now is a many-to-many RNN, in which it takes multiple inputs and gives multiple outputs. So one example that I can give over here of a many-to-many RNN is the language translator. So if we are giving in some kind of inputs in a certain language and we want its translation in a different language, see, let's say for example from English to Hindi. So if I'm saying hi, my name is Rohan, so it will take hi, my name is Rohan like that and give it respective translation in the output. Now because I want my model to show all these kind of outputs, I am going to use this many to many version of the RNN. Now, there are again a different kind of RNNs. One of the other things that comes to my mind right now is the many to one. Now, in many to one, we don't give the outputs of the respective time steps. What we are instead doing is we just pass in that outputs to the next time step, and then only the last time step is what we are going to present as the output. All these things are not visible. Only this last thing is visible, and that's how it becomes many inputs are taken inside this one RNN unit, and then it gives only one output. Now, one of the example that we can relate over here is the sentiment analysis. So what happens over here is, for example, let's just assume that few weeks back you had ordered certain kind of product from an online company, and now after using it, you want to write a review on it. So now, depending on the words that you are going to select in order to write your review, all these kind of words are going to be acting as the input for this kind of models. And then depending on certain kind of keywords inside it, for example, let's say that this product was pretty much useful for you, so you will be writing something like, this is an amazing product, these are the kind of benefits that I had after using it. So this keywords like amazing product and the benefits, all these things is going to help this model understand that this particular review is a positive one. So that's how a many to one RNN work. It takes in different kind of inputs, and then based on it will give a certain output. So that's about how a basic RNN unit works. However, this kind of RNNs are also having some kind of drawbacks associated with it. And one of the main problem is that it is not capable to remember information for the long period of time. So if you are having a longer data that this is going to take as an input, it will not be able to retain information of what you have written earlier. So just because we are talking about the sentiment analysis, let's just again take one example where you are again ordering a product, and this time this product was not satisfactory and you had a overall bad experience. Now because you are a genuine customer, if there were certain things that was also useful for you, you will also be writing about it, but the overall experience that you had was pretty much bad. That's what I want to write in the review. So this time what's going to happen is, let's say that initially you started writing all the things that you found bad about the product, you are expressing your anger towards it, and at the end you are also writing certain things that you found useful. But now what's going to happen is, because RNNs are prone towards not remembering information for a longer period of time, it is just going to skip all the things that you have written earlier, and just based on the last few lines where you have written something good about it, it will say, either depending on, let's say that in only one sentence you're writing something good and the previous sentence was something bad, so it will consider it as a neutral sentiment of yours. But let's say at the end you're writing, let's say 2 or 3 sentences, so in that case it will consider it as a positive sentiment, but the overall product was not satisfactory for you. So that is the main problem associated with this kind of RNNs. But now what is the logic behind why are this kind of RNN units not able to retain information for a longer period of time? So the answer lies in the back propagation step. So what happens inside the back propagation step? This is where the model parameters are actually updated with some kind of optimizing algorithm. And most of the popular algorithms that you will be using nowadays is having some kind of an idea of gradient descent. Now, what is the gradient descent? For that, what I'll do is I'll just open a new tab, and over here I've already searched about what a gradient descent algorithm is. So over here, what happens is I'm trying to update my model parameter by using the previous value that I had in the previous epoch. Initially, I'll just have some kind of a guess value, and after each and every epoch, I'll just keep on using the previous values and update these new values of the parameter until the maximum value has been achieved. So when is the maximum value achieved? When this value will become negligible, when the change in the loss with respect to that parameter is negligible. So inside this gradient descent technique, the basic idea is, if I just open this curve, Over here, this is the loss or the total summation of loss, or we also call it as a cost function. So our goal is to minimize this cost function as much as possible and get the minimum value of the cost. And this is only possible like by taking the derivative of cost with respect to that parameter. So if that value becomes almost zero, so we are getting closer and closer to this particular point. So when this value becomes closer to zero, we are assuming that this x is basically now at the optimal value. And that's where we say that, okay, now my model parameter has been learned properly. But now what happens inside this is, now because the weights over here are shared, because you know over here we are doing the back propagation through time, because for each and every time step we are having different things going on. So now for, let's say, if I'm computing the derivative of loss with respect to this output, now this output is having so many different inputs in itself. This is the input one, the previous value of the output was now also fed over here is the input, and now over for this particular output, this was the output that was used, right? So this kind of multiple things going on together overall creates a long gradient multiplications. And if one of the gradients becomes negligible, if one of these values becomes negligible, all of the values will become zero, and the final updation will not be able to happen if this becomes zero. So this is just a rough idea to make you understand that this is what we call as the vanishing gradients, that your gradients are just going to vanish if one of the values of the gradient becomes negligible. And that's the main reason why our models are not able to, or the RNN model is not able to remember information for a longer period of time. So if you want to look into the gradient multiplications, this is one of the PDF that we have used inside one of our training programs that had taught the ideas about the RNN. So if you want, you can just go through it. The main part, that the important part, is the last one, derivative of loss with respect to the weights of the hidden layer, the output layer, and the input layer. So that's the kind of the derivative of loss that we are having. And we can see that there are a bunch of things multiplied over here, a bunch of things multiplied over here. So if any of these derivatives goes to zero, it will just mean that all of the other things will also become zero, and the overall updation of this thing will not be able to happen. And that's the main logic. If you want, you can just scroll through this. Obviously, you will not be able to understand this if you are not aware about how the gradient descent or any kind of differentiation techniques are going to work over here. But anyway, the main point was to show you that these are the kind of the derivatives that you will be having. And now when you will be updating this, you will be doing dl by dw multiplied by with a learning rate, and just update the parameters with the help of the algorithm that we just saw. And as I mentioned, in most of the optimizers that we'll be using, the popular ones nowadays that you'll be using has some kind of a very minute amount of gradients happening somewhere here and there. So that's the main reason why vanishing gradients are a huge problem with the RNN. Now, to overcome this issue and retain information from past for the longer period of time, we are choosing LSTM networks, or else long short-term memory networks, whatever you want to call. Now, this was constructed specifically to overcome this vanishing gradients problem. Now, here the mechanism of LSTM is done with the help of the gate mechanism. Now, this kind of gates are responsible for the LSTM networks in order to retain information for a longer period of time. So if I just scroll below, see, now GRU is something that we'll be not talking in detail in this particular project, but the basic idea about the RNN is that it contains only one neural network. Inside LSTM, there are 4 different neural networks, and all of this is acting like a gate. So there are main 3 gates over here because of which LSTMs are able to remember for a longer period of time. One is the forget gate, the second is the input gate, and the last one is the output gate. So the basic rule of this forget gate is whatever, see, now inside this whole LSTM cell, the first thing that you need to keep in mind is the memory from all the previous time steps until the last time step will be stored inside this memory state or the cell state. There are 2 different names given to the same thing. C refers for the cell, so cell state, but it does the job of the memory. So all the memory from start till the end will be stored in the cell state. So now what's happening over here is this forget gate. What's happening in the forget gate? I'm taking the input from the current layer and also from the previous hidden state. I'm applying sigmoid on it. And then because applying sigmoid on it and based on some threshold value, our values will be either 0 or 1. So if the value is 0, so from previous time steps, all the values that is multiplied by 0 are to be forgotten. and all the information from the previous state multiplied by 1 are to be something to be retained from the previous time steps. So that's the role of this forget gate. Whatever information that I want to forget from the previous time step will be multiplied by 0, and the things I want to retain will be multiplied by 1. And how am I getting the 0 and 1? With help of the current inputs and the previous cell state or the previous hidden state inputs. So that's how we are getting the output over here of the forget gate. So forget gate is nothing but the sigmoid of, obviously there are some weight associated with this particular forget gate. So we are saying that WF, that is the weights associated with the forget gate, taking the inputs of the previous hidden state and the current input state, concatenate them together, also at the bias of the forget gate, and that's how we'll be, after implementing the sigmoid layer on it, we'll be getting the forget gate. And now similarly for the input gate, what is the inputs that I want my this particular time step to remember, and I'll simply concatenate them with the previous inputs after, like in the cell state I know that it is containing the only information that now it wants to retain from the past. All the thing that I want it to forget is already been forgotten. So that information from the past along with the current information will be added over here. So that is where I am just collecting the information from past as well as from the current step, and that's where I'm going to pass it ahead in the output gate. And inside this output gate, again, whatever the inputs I'll be passing in, it will be having the values in between 0 and 1. And if we are setting the threshold, we'll just get two values, either 0 or 1. So out of this cell state, okay, the cell state, after concatenating the stuff from the, like, what are the stuff to forget and what are the stuff to remember, and after adding the current data, if I want to now get the output of the hidden state for the next time step, what I'm doing is I'm using that cell state value that I'm having by multiplying the forget gate with the previous cell state and current input with the candidate state. Now, candidate state is nothing but this is where the inputs are basically fed over here. This sigmoid layer on the input gate is again going to get the values either 0 or 1. So whatever values are multiplied by 0 in the candidate state are something not to be used as the input in this current time step, and any values that is multiplied by 1 in the candidate state are the values to be passed as the input in the cell state. So that's what is the job of this candidate state. So candidate state is going to be having the values of the input, and then after concatenating it, it now is going to pass through another 10H layer over here, and then is going to be multiplied by the, again, the values of 0 and 1. So in this output, again, the things that I want as an output as the hidden state is going to be multiplied by 1, and if I don't want something as an output, it will be multiplied by 0, and that is all taken care with the help of this sigmoid layer on this output that we have created. This is the basics of how LSTM work. And if you can notice, there are a lot of parameters that this particular LSTM networks are going to learn, and depending on if you are creating stacked LSTM layers, just imagine the number of parameters that we'll be having. If I just show you, like, if I just scroll below, if I show the amount of parameters that we are having in just using 2 LSTM layers, we are getting about 600k by using only 2 LSTM layers, right? So now that's the basic idea, that LSTM creates a lot of parameters, and that's the reason why the time to train our model basically increases inside the LSTM. And now, in order to solve this time issue, now we are having a new variant of LSTM that is called gated recurrent unit. It was invented about a decade ago, and it consists of only 2 gates now. It consists of only 2 gates. One is called the update gate and the other one is called the reset gate. The basic process is exactly same as what happens in the LSTM, but now instead of 3, only 2 gates are going to be enough in order to do the job. And now, because the number of gates and the things going on inside the GRU is pretty much less as compared to LSTM, the number of parameters overall for GRU will always be less as compared to LSTM. And therefore, that's how this GRU will be able to learn in a faster way, and it will consume less memory as compared to the LSTM. And now, because in our particular dataset, we are only having about 3,600 datasets, 3,600 something it was there. I'm not exactly sure the number. But yeah, because the data points are pretty much less, we can do our job with the help of LSTM. Just one thing that you need to keep in mind is, while we'll be training our data, you just keep this accelerator, change this accelerator from none to this GPU. All right, and just keep in mind that this quota that we are having is only for 33 hours for a week. Like this kind of hours will keep on changing depending on the demand of this particular GPUs. But just keep in mind that you are not exceeding this. And yeah, if you don't choose this GPU, it will take a lot of time again to run this kind of model training. And therefore, it is recommended for you to turn on this GPU in order to have a faster output. So that's one thing that we are doing. I will not be repeating it ahead, but just I'm already starting it over here, and therefore, while running this whole coding cell, it will automatically use these GPUs instead of the CPU. So now, because I'm done with the whole thing, I can stop it. But yeah, because I'm not having any kind of different project for this particular week, I'll just keep it on. There is no issues with it. But yeah, that was a basic idea about, like, what is the RN and how is it different from LSTM and GRU. And now, if you want, there are some different blogs that I have mentioned over here, which can help you understand LSTM in a more detailed fashion. So let's say that whatever I've explained is not making some sense to you, you need some more details on it. So this particular blog is pretty much useful. And the other one that you can refer to is this particular one, the extra resources on RN and LSTM and GRU. This is also pretty much good. You can use any of it. So yeah, that's about the basics of, like, how a sequence model basically works for the time series data with the help of RNN, LSTM, and GRU. And let us now go ahead and understand how we can transform the data that we are having into the format that LSTM will be able to understand it. So one thing that we need to keep in mind is LSTM layers expects a three-dimensional input. And currently what we are having is a one-dimensional input, something similar to what we can see in this image. So now we first need to understand how LSTM actually learns to forecast the data depending on the previous data. So we'll be talking about this, and based on this, we'll be able to convert this one-dimensional array into a three-dimensional array. So the basic process of what goes inside this LSTM is, for the univariate time series analysis or the time series forecasting, we create windows on the data that we are having. So this particular data is containing how many values? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is containing 9 different values. Now what I am going to do is, I'm going to create a window, and I will be feeding these values as an input to my model and say that now with help of these values, learn how to predict the next value. So the value of 4, that is the sixth data set or the sixth point in this data, I want my model to learn this with the help of the previous 5 values. So this window is going to work like the training data, and this is just the training label that my model is going to learn to predict. So similarly, now what will happen is, because this window can slide by 1 unit, now this window will be taking new values inside it as 3 to 4. So from the values of 3, and I'm going till for all these new values, again 5 different values are used for training, and the next value is for the label. So this label is what, as I mentioned, my model is going to learn to predict or forecast. So that's how this kind of thing is basically going to work. So don't worry if you're not able to understand this in a proper way. I'll be showing you a live implementation of a random example. I'll be just, let's say, we'll be using the example for the Sunspot data itself. We'll be taking first 10 data points, and we'll be trying to create this kind of windows. But instead of choosing window size as 5, we'll be choosing a window size as 3. So in our case, what we'll be doing is, we'll be taking first 3 data points, and then we'll be predicting the value in the fourth point, and then again slide our window by 1 unit. Then this next 3 will be the part of the training data, and the next value is what will be the part of prediction, that using these 3 values predict the next value. So this is what we are going to do for our example to understand it in a better way. So this basically, this whole function that we are going to use for this particular project is directly taken from Coursera. This is the helper function that they had for their particular course on time series analysis. So this is not just one way to do it. There are multiple ways to do it. With help of for loop, you can create your own function that will work similar to what I have just explained over here. Now, this is one of the tasks that I am having for you to do, that you will be creating a function which will be taking this kind of data set, a one-dimensional data set, and now your function will output or return the three-dimensional input that LSTM will be able to understand. It's very much similar to what I'm going to explain right now. So inside this window data set, what I'm passing is, I'm passing the series. So the series is nothing but the Sunspot data for our case. This window size is what is the amount of sequence that we want to use for training purpose. And then batch size, I'll be talking about the batch size in a while. And then the shuffle buffer also I'll be talking in a while. So in order to understand what are the steps done over here, I'll be taking you for individual steps and help you understand what does each and every line is going to do. And then based on that, we are just going to create this function, and we are just going to simply use it to create different kind of batches like this. And that's how we'll be able to create a data set that our LSTMs will be able to understand. So let's just go ahead and break down the above function to understand what exactly is happening. So for example, we are taking the first 10 example, as I mentioned, from the Sunspot series that we had created earlier. So I'm taking that Sunspot series and taking the first 10 values and that dot values, this time series, I'm using dot values on it. It will convert it into a NumPy array. Now this the panda series is now converted to array. Now what we can do is we can just look into the shape of it. So I'm just printing what is the first 10 values of the data and what is the shape of it. So see, this is what it is. The first 10 values in our data set for the sunspots starting from the January, February, March, April, from 1749. These are the values that we are having, okay, for the first 10 months. And basically this is the shape that we are having. It is containing 10 rows and that's it. And now what we are trying to do is we are trying to convert it into a two-dimensional array now. So for that, what I'm going to do is I'm going to add an extra dimension over here. So it should be 10,1. I want to shift this row vector to a column vector. And how am I going to do it? Actually a column matrix. So how am I going to do that? I'm going to take this dumb series. This is nothing but the dummy series. So I'm going to take the dummy series and take all the values of it, like it is containing all these 10 values. So I'm going to continue taking all these values and then add a new axis. This np.new axis is simply going to create an extra dimension where we use this np.new axis. So for example, if I'm using this np.new axis after this again, so it will give me a shape of 10,1,1. So that's how this np.new axis is used. It just adds an extra dimension to our data. So after doing this, that's how our data is going to look like. Now this row vector is converted to the column matrix, that inside this one whole array, we are having one full column of data. And that's why the shape now is 10,1. That new axis is adding this extra dimension. Now, to use the Windows method of TensorFlow to generate the sequence for LSTM, we need to create tensors from this NumPy array. So now, in order to use the window, like the method that we are using over here to create this kind of window, we are taking help of TensorFlow. As I mentioned, you can do it in any way that you want to do it. But right now, we are using window method of TensorFlow. So in order to do that, I'll have to first of all convert my data. I'll have to convert my data into the from NumPy array to tensor. So how will I do it? I'll be using dataset as the variable and say that from TensorFlow.data.dataset, from tensor slices, I want this NumPy array to convert into the tensors. And then in order to visualize this tensors, what I'm going to do is, for something in this data set, I want to see, like for tensors in the data set, that's what I should say, not something. So for tensors in the data set, I want to see what are the tensors that has been created inside that bunch of tensors. So for that, what I'm doing is I'm just printing that value, and these are the kind of tensors that we are having. So you can see that this array is just converted into the bunch of different tensors. 96.7, 104.3, all these values are just repeated, but now in the form of tensor. And now what we are going to do is we are going to generate the sequence of length 3 or a window of size 3. And then the next value will be the one which I want my model to learn and predict or forecast it. So for what I'm trying to say is these 3 values will be creating one window, and this 92.8 is what I want my model to learn it. So what's going to happen over here? I'm going to choose my window size as 3. And then using this TensorFlow's method of window, I'm using this previous values of this data set because it contains the tensor. And then on this data, I'm using dot window with the size of window plus 1, like window size plus 1. Like what is the purpose of this plus 1? Because now see, what I'm going to do is I'm going to create a window of 4. And then I'll be just splitting the window of 4 such that, like, the first 3 will be the part of the training and this one will be the part of the thing that my model needs to predict. So you will be understanding once you will be seeing what I'm trying to achieve over here. So this plus 4 is basically going to first of all create a window of size 4. You must be having this question that we are choosing this window size as 3, then now why are we doing window size plus 1? You will just understand it in a while. Now this shift equals to 1, this basically means that what is the shift that my window should have across the data. And then this drop remainder equal to true will just ensure that the shape of the tensors that will be created will be just same. Now again displaying the changes after doing this shape is, see, this is what we are trying to get. This 96.7, 104.3, 11, 106.7 and 92.8. Now this is one full window. Okay, now this is one full window. Now you can see that again the value is starting from 104, then again 116, again 92, and then again this is the new value 141.7. Now again my data will continue from this third point. I'm keep on sliding my windows by one unit. And now what I want to do is the window of 4 that I have created, I want first 3 values to be splitted and the last value to be splitted. So because we know that the first 3 values is what we want, because we have chosen the window size as 3. So I want my first 3 values to be a part of the training data, and this value in the training data, I want it to be a label that my model needs to predict or learn to predict for now while training, right? So that's the basic idea that what I'm trying to do in the next step. So this, in order to do so, what I'm going to do is I'm going to use flat map first of all. So I'm just going to, because I'm having the batch of 4, right? I'm going to perform flat map on that 3 plus 1, that is the batch of 4. And then after flatting all, so flatting is nothing but going to create this windows of 4 all together. Okay, after doing that, creating this windows all together, it will now take all the values till the last value. Like it will not include the last value, but all the values before the last value, I want to split it into one tensor, and the other tensor will be the last value in that particular window. So this W, I'm just using my lambda function for both of the step. So over here, I'm creating the batch of 4. So out of this data that we had created earlier, I'm creating the batches of 4, 4. I'm creating different batches of 4, 4. And then again, using a lambda function on the same data set, after creating the batches, I'm going to take one batch, whatever is the first 3 values, I'm going to shift it to one tensor, and the other tensor for the label will be having the last value of that previous batch that we had created or a window that we had created. So that's how this is going to work. So if I now show you the data, we can see that now 96.7, 104.3 and 116.7, this is one window that we are having, one sequence of data that my model is going to take and learn to predict the next value, that is 92.8. Now the window will be sliding by 1 unit, and now we are having 104.3, 116.7, and now 92.8 is going to be part of the training data in order to predict the next value, that is 141.7. And again, this will keep on going. Now again 116.7, 92.8. Now this 141.7 is a part of the training data in order to predict the next value, that is 139.2. So we have created our batches like this. And now what we are going to do is I'm going to use a line that is ds.batch.prefetch. Now just remember one thing, I'm just trying to create one whole tensor of this data which contains all this kind of 3x1 shape, and another tensor for it will just contain all the labels together. So for that I'm using this line. Now one thing that we need to keep in mind is the total data that we are having is the size of 10, and because we are creating the window of 3, the maximum batch that we can create for the training batch particularly will be 7. We cannot create more than 7 batches. 7 is the maximum value. So instead of writing 10 over here, I could have also written 7, but just for the demonstration purpose. Like what is going to happen if you exceed the value of 7 for the batch? It will simply go ahead and create the maximum available batches that it can have. So we can see that the shape that we are having, this is called the batch size. So batch size is 7 now. There is a total of 7 batches of different values inside it of shape 3x1. So this is 3x1 training data. This is a 3x1 training data. This is another 3x1 training data. Now what I'm going to do is I'm going to take this data, feed it to my model, and it will help my model to predict or learn to predict this kind of values, that is 92.8, 144.7, 141.7. All these kind of values are nothing but the labels. So based on this, the back propagation will work. And yeah, that's how this learning process will keep on continuing as any kind of other neural networks. And yes, this is how we are preparing our whole data set in order for our LSTMs to understand. So that's why we are creating this whole helper function for generating this training data for LSTM. using this window method. Now, as I had mentioned, you can create the same exact thing with the help of for loop as well, or any kind of other method that comes to your mind. And this is one of the tasks for this project. So you can just go ahead and see how you can create, like take this one dimensional data, okay, this one dimensional data of Sunspot, how you can convert it with different kind of batch size and the training samples of the shape, anything that is like, provided by a user. Try to create a function like that. Okay, that's your basic task. Now let us just go ahead and see how we can create a function to forecast this kind of things. Like I'll be passing in the validation data set. So in the validation data set, my model is going to just understand, okay, now this is the part of the values that I'm having. The previous values are, this is the window size. This is the window size. Now just see that I am not using +1 over here, because now I don't want the fourth value to be included. I just want the three values and I want to predict what will be the next value in the data set. So that's what I'm doing over here. All the steps are just same until the last step. In the last step, I'm just saying that now I want I want to use the model that I have created of LSTM in order to predict the next value in every batches that we have created of some size. For example, in this we are talking about 3x1. So for each 3x1, I'm going to take this individually and I want to predict this next values. So that's what is going to happen in the model.forecast or model_forecast. Okay, so there is nothing much to explain over here. And now we can finally go ahead and create a train test split. So we are going to create the data that we are having. We are going to split it into the training part and the validation part. So now, because I've already created the Sunspot data earlier, but just to take it in a normal way that we do in the LSTM, that is, we use series and time. So series is nothing but the monthly mean total sunspot numbers, the same thing that we had done earlier where we had created the sunspots data, right? Sunspots is equal to the same thing. And dot values is just going to convert it into a one-dimensional array. And then time is nothing but the values that we are having in the first column, that is the index column that we are already having, starting from 0 all the way to 3264. And again, I'm also converting that to values. Even if I don't do it, even if I don't just do this step, even that will be fine. But just for the completeness of this project, I'm just doing extremely step by step. So now splitting this data into the training set. So I'm keeping my 90% of the original data for the training and the remaining data for the validation. So first of all, I'm using what is the total length of the series. What is the total length? It will be 3265 as we know. And then if I'm multiplying it with the 90% and converting it to the integer, whatever is the integer value that I'm getting after doing this, I'm going to take first data from the 0 index till that particular time that we have created. The 90% of the data will be stored from 0 to that particular value. And all the value after that will be part of the validation data. So we are creating the time data, also the time train, time validation, also the X train and X validation. So X train and X validation are having the values of multiple batches of this kind of sizes that we are going to pass into the model. And time is containing the values from 0 to 3264. So that's the basic idea. And that's how we have splitted our data. The first 90% of the data is used for training and the remaining 10% is used for validating the thing. And now there are now bunch of parameters that you should know. But now many of the things you will not be able to know because we have not either learned or discussed about it as of now. And some things that you can understand over here is the window size and the batch size. Now where we are going to use it, if I just scroll above, we know that we have created with the help of this window dataset function this kind of data for our LSTM. So what is going to contain? This is called, for LSTM, the first thing is called batch size, the second thing is called window size, and the last thing is the number of features. Now because in the time series data that we are having right now is the univariate time series, it means that we are only having one single feature to use and predict the next values, right? So that's the reason why we are choosing the number of features as one. That's it. Now if we are having two features like that to predict, so you will say that the number of features are 2 in that case. So depending on that, you choose the last number. You can just manipulate it to the number that you want to create. But right now, because we are having a univariate time series, we are just keeping that number as 1. This 3 is the window size that we are having, and this 7 is nothing but the batch size. Now, if I'm using over here the batch size as, let's say, something less than 6, something less than 7. So in that case, what's going to happen is it's going to create different tensors. So if I'm using over here the batch size of 6, it's going to create the batch of shape 6 comma 3 comma 1 instead of 7 comma 3 comma 1, and all the remaining things will just go to the next batch. So that's how this kind of things work. So yeah, depending on what kind of batch size that you are giving, you will be creating multiple tensors. And similarly over here, because we are having 3265 data points, out of which we have created 90% for the training data. So in the training data, I am going to create the batches of 145. So this kind of different batches I'll be having, and I'll be training that batches, and then the window size that I am choosing for this particular project is 60. You can obviously go ahead and just change this kind of parameters and see how your model is performing. But yes, these are the two things that you are knowing as of now, the window size and batch size. This is something that is going to be helpful in order to create data like this. Then what is this shuffle buffer size? This shuffle buffer size, I have not talked about it, but we have used it over here while creating this window dataset. We had used it over here. Now why I didn't show you this in our this breakdown process, because you will be just confused of what is happening. But now this is the time where I can explain the usage of this ds.shuffle with the shuffle buffer size. So this shuffle buffer size is just going to help this tensors to just shuffle in a random order. So after using it, what will happen is, after using that shuffle buffer size, it's just going to shuffle these things randomly. So let's say that this thing can come down and this thing can go up. Any kind of order, it will just shift. And accordingly, this another tensor, the label tensor, is also going to shift in the same way. So if this whole 3 cross 1 goes to the last point and this goes to the first point, then this 92.8 will come down and 125.8 will go up. It just to the purpose of doing this shuffle is to reduce the variance and make sure that the model remains general and overfits in less amount, because LSTMs are prone to overfit. So this is just one step that we are doing to reduce the variance and making sure that it does not overfit more. So that's the very basic idea about what shuffle buffer size is. Just that you use different values, it will be shuffling it in a random way according to that. So coming back to where we were, all the other things like delta is going to be used for the Hubbard loss. So I'll just go ahead and just write down the things over here that you will be using this for, where you will be using this. So this is for the Hubbard loss. Hubbard loss is something that I'm going to just talk about in a while. Then window size and batch size, both of them are going to be used for the LSTM dataset, or just for dataset. That's what I'm writing over here, for dataset. And then batch size again is for the dataset. This shuffle buffer size is for shuffling the data, shuffling the data set randomly. And then epochs. These epochs are used. Now see, there are two different kind of epochs that I have used. These epochs are basically used in order to choose the optimal learning rate. You will not be understanding as of now, but let me just write it over here so that I don't have to write it again over there. So for optimal learning rate, and then this next epoch is going to be the training epoch. So once I'm sure like what is the learning rate that I'm going to use with the help of the optimal learning rate epochs, I am going to add some extra epochs on it, and this will be now the training epoch. So if I'm using 100 epochs for understanding what is the optimal learning rate, I'm going to add extra 100 epochs for my model to train on this epoch. So these are the training epochs. And now obviously you can go ahead and change all these values. Now this momentum SGD is the, like while using the stochastic gradient descent, we are going to use a momentum. And what is this? I'll be explaining you that. But for now, let me just write that for optimizer. And what is the purpose of it? I'll be explaining you that in a while. And let me just, for the completeness, just copy this and paste it in the line below. So yes, that's it. Now you are having the whole idea about where we are actually using these parameters. And if you want, you can include obviously more parameters, but these were just the basic parameters that came in my mind, and that's what I've written over here. You can add more things over here and keep on changing the things and see which one is going to give you the better result. But for the basic things, I'm just using this bunch of parameters. So now there are total of, after doing the split, we can say that there are total of 2,938 training samples and 327 validation samples. So this was all about splitting the data set and writing the parameters in order to start building our model. But in building the model, there is something that we need to keep in mind. what is the optimizer that we are using and what is the loss we are using. So the for the time series data that we usually use is the stochastic gradient descent. So that is what we are going to use. And for the loss, we are specifically choosing for this particular use case Hubbard loss, because we know that this data is containing a bunch of outliers, right? So Hubbard loss is less sensitive to this kind of, where is it? Yes, over here. So Hubbard loss is less sensitive to this kind of outliers in the data, and that's the reason that we are choosing it. So what happens in this Hubbard loss? If the error, so whenever we are going to take the value, like after doing the learning process, it's going to give some kind of prediction, and the actual value, we take the difference of it, take square of it and multiply it by half. This is nothing but the mean squared error. This is nothing but the advanced version of the absolute error. So we are telling this loss that if the difference between the actual value and the predicted value is less than a particular value delta, then use the mean squared error. And if the delta value is greater than this difference of actual and the predicted value, the modulus of that value, then use the advanced version of this absolute error. So this is nothing but just, that's how the Hubbard loss works. And that's, if you want to see it from this image, this is the mean squared error. And this green thing over here, this green thing is nothing but it's showing that for the values, if the delta values are greater than 1, then it's going to take the straight line shape. And then if the values of delta is less than 1, then we can see it is taking this kind of a square kind of shape. So that's what happens. By default, Keras is having in the Hubbard loss the value of delta is 1. You can simply go ahead and try to play with this value, and that's the reason that I kept this parameter of delta as 1 over here. You can go ahead and change it to, like, 0.8, 0. Whatever it is, it's totally up to you. Like, what is the limit that you want to have in order to choose the MSE and in order to choose this advanced version of the MAE. So these are just the basic details about, like, what are the other things that is part of the Hubbard loss. But overall, I just explained you what is the reason that we are choosing the Hubbard loss, and that's what you should know. So now it's time to go ahead and build the model and find the best learning rate to optimize the model training. So what I'm going to do over here is I'm going to create a hybrid model. Now, what is the meaning of hybrid model? We are just trying to just connect bunch of different layers along with LSTM so that my model is learning effectively. And first of all, what we are trying to do is we are trying to use from the callbacks the learning rate scheduler. It's going to take different values of learning rate based on which it's going to learn and compute the loss. And now our job is to understand, out of all these learning rates that we have created on which we are doing the training, in which out of all this we are getting a smooth training with the minimum loss, and that will be our optimal learning rate. So that's what we are going to figure out by looking at the results after running this cell. But let us understand what actually are we using in this coding cell. We are starting with tf.keras.backend.clear session. This is useful just in case if you are forgetting to restart the whole kernel and you just keep on rerunning the cell. It's just that you to have enough memory to run these models, we are using this step. And in this next step, we are creating the seed for TensorFlow and NumPy. This is just going to ensure that every time we run this coding cell, we have same kind of randomness. And then this is where we are creating the actual training data for our model. So we know that window dataset is that function that we created in order to build this training set. So we are passing in the series that we want this kind of window dataset to be generated with a mentioned window size as 60 as we had defined earlier, batch size of 145, and shuffle buffer size is just going to shuffle this data randomly depending on the value that you are choosing over here. So that's how we'll be creating the training set over here. If you want now, you can just go ahead and also try and run this kind of for loop and see, like, for I in training data, for value in that I, what is the value, and you will be able to see this kind of data that will be generated with the batch size of 145, the window size is 60, and the feature value as 1. That's what we'll be able to see. And so if you want to visualize it, I'm leaving it up to you, that you can just create one more line over here and visualize the data in the output. And now that's where we are building the model now with the help of the sequential API in the Keras. So first of all, I'm using the convolution 1D layer. Now, what is the convolution layer? I have explained this very well in the previous project. So if you're not aware about it, you can just go ahead and look into the project and come back over here after you know that, okay, what is the convolution layer? So we are basically using this convolution layer over here in order to smoothen out the input of the time series. So initially, if you remember, the data that we were having was pretty much noisy, right? This data is pretty much noisy. So in order to smoothen it out, I'm using the convolution 1D layer with the total filters as 132, the kernel size is 4, stride is 1, padding is casual, activation is ReLU, and the input shape is none comma 1. The reason that I'm using none over here is so that, see, batch size is also none and the window size is also none. So automatically it's going to take the value that we'll be providing. And you will be understanding it by after running, like, after running the cell, you go to the training data, you will be able to understand what is the actual shape that it will be taking. And the feature size, sorry, not the feature size, but the number of features that we are having is 1. So that's why I'm just using 1 over here. And that's how we are defining the input shape of this model. And then after this convolution 1D layer, we are starting with the stacked LSTM layer. Now, what is the meaning of the stacked LSTM layer? See, there are a number of units that we are passing is 256. And for the second layer, we are passing 132 different units. So after, see, the units, what we had seen over here for the simple RNN or the LSTM over here, this is 1 unit. So I'm choosing different 256 and 132 units over here, as we can see in the model that we had created over here. So that is the units, the number of units that we are using. Now, what is this written sequence is equal to true? It will now be acting as, like, say if I'm doing written sequence is equal to true, this is what I'll be able to get, that for each and every time step I'm returning the output. If I say that this is false, it will just give me the output of the final time step. So in order to because in order to create the stacked LSTM, that we want to create bunch of LSTMs onto other LSTMs, what I am doing is I'm saying the written sequence equal to true over here. It's going to take all the outputs of different time steps and feed it to the next LSTM layer with 132 different units. And now after this layer, I'm keeping that written sequence as false, so that now I can directly pass it to the dense layer. Dense layer is nothing but the fully collected layers, and it is just going to help us create our values in a way that our model is able to finally predict only one value out of it. So starting from this 132 units of LSTM, I'm passing it to the next 80 in the next dense layer, then the 10 in another dense layer, and the final one, the value that I want to predict is only 1. So I'm just creating 1 unit in the final layer. And then this lambda layer is just going to push these values, whatever values that we are using, in the range in the original data set. In the original data set, we had seen that the values are lying in between 1 to 400, right? 1 to around 400. So that's the reason why I'm taking whatever is the value that I got after all these steps, because I know that I'm using different activation functions, and the activation functions inside the LSTMs is the 10H. It basically takes the value in between -1 and 1. So that's the reason why I'm using the 400 over here. It's going to push the original data into the range that we want for our particular use case. That's the reason why I'm using 400 over here. Whatever will be the value multiplied with 400. And now comes the displaying the model summary. So that's what is the summary that we are having. So using this convolution multi, LSTM, all these kind of parameters and all these things we are having, the total number of parameters are around 600k. Right? These are the trainable parameters that we are having. And then this is where we are creating the learning rate schedule. We are using the callbacks. And how am I creating this? You will be able to understand it really well. I'll be individually doing the step in order to show you what are the kind of learning rates that we are using. But the basic idea is we are going to start with the 1e to the power of -8. And then every time the new learning rate that I want is I'm going to simply multiply it with 10 to the power of whatever is the epoch number, starting from 0 all the way up to the epochs that I have chosen. So using this epochs, I'll just divide it by 20, and the next values that I'll be getting for the learning rate. So as you can see, the first learning rate would be what? The starting learning rate, that is 1e to the power of -8. And then I multiply it with 10 to the power of 0 by 20. The next learning rate will be the starting learning rate multiplied by 10 to the power of 1 by 20. All these values are the way how my learning rates are going to change. So that's how my learning rate schedule is going to work. And for all this kind of learning rates, we'll be getting certain kind of outputs, and that outputs is what we're going to plot later on. But now we are using the stochastic gradient descent for the optimizing technique, and we are choosing the initial learning rate as 1e -8. And this momentum over here, this momentum is equals to momentum SGD. So this momentum is what we are using, the momentum that we had used in the earlier while defining the parameters. Where is it? Yeah, over here, the momentum SGD. This is just going to ensure that our model is converging in a faster way. You can just try different values of momentum, and you can just get different results. And you see by yourself how by changing this momentum value, how you are getting different values as the output. All right. So with that being said, where were we? Yeah, over here. So after that, we are just compiling the model with the Hubbard loss with the delta value as 1, optimizer as this optimizer SGD. And metric that I'm using to monitor is the mean absolute error. That's what I'm trying to monitor. And then after this, I'm going to start my training process over here. I'm creating this history variable, which is going to store all the history of this training. So starting with, I'm passing the training set, the number of epochs, and the callbacks is the learning rate scheduler. So this is just going to give me the output. And the final thing that I'll be getting out of this is what I'm going to plot over here. You will be understanding what is this plot. But before that, let me just explain you what is the thing that I've done over here. Now, so you can either do, from this history that we have created, we can do history of learning rate and do the same thing. But now, because I really wanted to show you what exactly we are doing in a proper way, I am just doing this extra step over here. So over here, I am having the starting learning rate, and then I'm multiplying it with 10 to the power of the epochs that we are having. I'm see this np.arrange this epochs is just going to create the array, a one-dimensional array from 0 to the last value of the epoch. And I'm just simply dividing it by 20 because that's exactly what we have done over here. So it will start taking the values of epochs from 0, 1, 2, all the way up to the epochs that we have chosen. And that's how it will give me the learning rate. Starting from 1 e power of minus 8, the next value is 1.12 e power of minus 8. And all the time you can see that the learning rate is just the powers that we are having is starting from minus 8, then it's going to minus 7, then minus 6, then minus 5, all the way up to minus 4. So this is the way how my learning rate is changing, and depending on that we have been getting this above result. And now our task is to find on what value we got the minimum loss. So for that, I'm using this extra steps over here. Or else you can directly go ahead and plot this data and directly figure out that, okay, yeah, over here, after this particular step, the learning part is again not stable. And this is the place where it is a bit stable. And this is where we are getting the minimum amount of losses over the minimum amount of loss that over here. And this is at 2 e power of minus 6. So that is the optimal learning rate that we have found. And we'll be using it again in the same model that we have created over here. If you want, you can just create a function out of it so that you don't have to reuse it. But what I have done is I have simply went ahead and copied this and pasted it over here. And then I'm just using this optimal learning rate. Everything else is just same. I'm not doing any difference. I'm not doing any kind of changes over here. The only one thing is I'm choosing the optimal learning rate over here without any kind of callbacks now. And directly I'm doing the training of the model and see what is the kind of output that we'll be getting out of it. So let me just take you back for a while and help you understand what have I done after creating this learning rates. So after this, I just went ahead to find out what is the optimal value of learning rate and how have I done it. So by using this history that we had created over here, after fitting, this training part was done for just finding out the optimal value of the learning rate. Okay, this is not where we are doing the actual training. This is just done for the understanding on which value of the learning rate will be getting the minimum amount of loss. So for that, what I'm doing is I'm using that history, and from that history, I'm tracking out the losses value. And then I'm finding what is the minimum value of that loss. That's what I'm storing in the minimum loss. And now I want to find that out of this, like this is the kind of an array that you will be getting for the loss as well. But instead of this learning rates, you will be having different values of the losses. And now in this loss, on which index I was having that minimum loss. For that, I'm using this particular step that inside that loss, what was the index of that value? And because that value is stored in the minimum loss, I'm passing it over here. So now this value is containing the value of the index where we got the minimum loss. And respectively, on what value of the learning rate we got that loss. I am able to track it with the help of, I'm going inside this learning rate array and using that index to figure out, okay, yeah, over here, by using this learning rate, we got the minimum amount of loss. So that's how we are getting the value of the optimal learning rate. And now all the other lines that you can see after this optimal learning rate is used so that my output over here of the learning rate that I'm showing, the optimal learning rate, is neat. Because over here, that's not the exact value. I just rounded off the first part. It was 2 point some different value, 2 point something e power of minus 6. But now just for my graph to look neat and clean, I'm just rounding it off. I was trying to work around the way using the round function, but I was not able to recollect any way at that point of time in order to do it efficiently. So I just went ahead and did these extra steps. Obviously, you can just skip this part and directly write the final value over here without doing that rounding off method. But just for my personal satisfaction, I had done this step. So if you want, you can just completely skip this step. And if you want, you can just go through it. I'm just writing a very basic Python things over here. What I'm doing is I'm taking because I know that the value is 2 point something e power of minus 6, what I'm doing is I'm converting this to a string, and then this is the first part that I'm getting. So that first part I want to round it off. So I'm doing that round off. So in order to first of all split, I need to convert this float value into the string. So that's the reason I'm converting that learning rate into the string. And then I'm splitting that learning rate at E. And the first value is what I want to round. And because I cannot round a string, I am again converting that string, that 2 point something, into a float, and then rounding it off, and then again converting that value to the string. Why am I again converting back to the string? Because I have to again join this whole values together. And for that, we need to use dot join method, and you will be understanding while I'll be explaining that part. And then the second value is this minus 0.6. That minus 0.6 is as it is. So over here, I'm not doing any kind of fancy thing. I'm just converting the learning rate to a string so that I can split it at E. And the last value that I'm having, that is minus 0.6, is what is stored inside the second variable. So the first variable is having the value of the initial part before E, but in a rounded off fashion now. The second value is containing the value after E, and then I'm creating a list in order to join that list together with the help of E. So this first value is nothing but 2. The last value is, the second value is minus 0.6, and I'm joining them together with the help of E. So in order to join this, this values that I'm writing over here must be in the format of strings. And that's the reason that why I converted my first and second variable in terms of string. So again, you can just skip this step, but yeah, just to explain it very briefly, I have done the steps in order to have a neat and clean version of the learning rate that has been displayed over here. And then I'm simply going ahead and directly plotting this graph of learning rates on x-axis and the losses that I got on the y-axis, and looking for the optimum learning rate. That's the heading that I have given. And yeah, this is the very basic thing. And the one thing that you can see new over here is the plt.annotate. Now this annotate is the reason why you can see this arrow over here. It is taking the value that I want to write over here, that is the learning rate equals to, I'm using the f-string method over here to take this float and just say 2 e power of minus 6. And then this value is nothing but to show what point that we are trying to locate. And over here, at where do you want to write this thing, on what location you want to write. And then just you're writing the arrow props as like, what is the face color you want. I'm choosing for the arrow, I'm choosing the black color. The width of it is 2, the head width is 8, and the font size over here is 12. That's what I'm doing with the help of plt.annotate. That is something new that we haven't seen anything like that till now. And also one more thing is this semi-log x. Like, why am I using a plt.semi-log x? Why not plt.plot? So now, because the learning rates are increasing exponentially, that we saw over here, like from minus 8 all the way to minus 4. So because of this learning rate are increasing exponentially, we are using for getting the optimal size plot over here like this, we are using semi-log x. It converts all the value of x into the log part of it, and then that's the reason why we are getting this kind of graph. If you don't do this, you will not be able to get the graph in this particular way. So to get this optimal sized graph, we are using the semi-log x on the learning rate. And yeah, that's it. I'm not doing any changes to the losses. The losses that we were getting were like, around starting from the 80 and going all the way till 56.48. So we can see that starting from 80 and going till 56 point something, right? So I'm not doing any changes with the y-axis, but for the x-axis, I am doing this change. And yeah, you can just try to look into how your graph looks without the semi-log x and with the semi-log x, and you will be able to see the difference. So that's about the plotting part. So that's nothing but pretty much fancy over here. And we can just look at over here, and we can see that over here the training was done smoothly, and then after that the training was again a bit unstable. And that's the reason that we are choosing that this particular point where we got the minimum value of the loss, and also that the training over here is smoothly done. That's the reason we are choosing this as the optimal value. And now using that, as I explained, using that same learning rate that we got over here, we are just everything else is same. Okay, I have not changed anything over here. Just I'm removing the comments, the model summary. Everything else is same, including this model.fit. Everything will be same, no difference at all. And then I'm starting my actual training over here, and using this optimal learning rate, I'll be able to get the best results. And that's the reason I had done the optimal learning rate thing with the help of the callbacks. And after doing this training, we can see this is the kind of losses that we are going to get. And again, I'm just like, keeping this track of the history so that we can do the plots necessary for this. And then these are the final results and the plots that we are getting after the training. So I'm just creating a variable for the metric and the loss from history. and then simply going ahead and plotting them together like this. We can see some kind of bumps over here and there, but it's pretty much normal for the real-time data that we are having. But if you want to go ahead and try one step further, try to smoothen it out by changing different parameters that we had created earlier. So this is the kind of the metric and the loss that it's going to change. The loss is also decreasing, the mean absolute error is also decreasing at the same time. So it's a pretty much good thing. That's what we wanted. And now in this next coding cell, we are simply calling this model underscore forecast function. And the first input it takes is the trained model. And in this trained model, we are just going to pass in the data set in terms of windows. And now we know that the model is trained with the window size cross 1. So all this series that I'm going to pass inside this model, I'm just adding that extra dimensions because I know that initially my series is nothing but the one-dimensional data. And that's the reason that I'm creating this extra dimension, so that the data that I'll be having of windows will be in the format of window size cross 1. And that's the windows that I'll be using to fit that inside this model. And this model is simply going to give me the next value that will be predicted based on the previous windows that we have passed as the input. So that's the whole idea about how the RNN forecast is going to work. Now you must be wondering that why are we passing in the whole series and not just the validation data? So for that, I'll just create one markdown cell over here and help you understand with the help of the dummy data. So I just created over here a dummy data. It contains the integers in between 1 to 10. And then randomly I've just splitted the data and said that the first 7 numbers are part of the training data and the remaining ones are the part of the validation data. Now assume that the window size is 4. Okay. Now just think about it. In order to get the first predicted values in order to compare it with the validation data, how will I get the data? By using the window size of 4 on the previous values. So I'll be using 4, 5, 6, 7 window in order to predict that next value. And that next value will be compared with the first value of the validation data. So if you can notice, we are taking in the values from this training data in order to predict my first value of the validation data. And then the next value of the validation data is also going to contain some of the values of the training data. So now my window size is going to be 4. So the next values that I'm having after starting the window by 1 unit is 5, 6, 7, 8. And now based on this 5, 6, 7, 8, I'm going to predict the next value. And now that will be compared with that second value in the training data, or sorry, the validation data. And similarly, the last window, that is nothing but the 6, 7, 8, 9. And that is going to give me the result that I'll be predicting, my model will be predicting and compared with this 10. So now these are the data that I'll be using, or my model will be using, in order to either compute the Hubbard loss or maybe the mean absolute error. Whatever you want to do it, we can do it. But now the thing that I want you to understand is, in order to predict this first value, we'll have to pass in the values from the training data. And that's the reason that why we are passing in the whole data set instead of just the validation data set. Because just imagine, if we just pass in this inside this RNN forecaster, what's going to happen? It's not even having enough data over here. If I'm saying that the window size is 4, it's not even having 4 data in itself. So how am I going to use it and predict the next value? So it doesn't make sense, right? And that's the reason that we are passing in this whole data. And now out of this whole data, what we are going to do is we are just going to choose some of the values that will be compared with this validation data set. Now, before we go ahead, there is one more thing that I want to bring it to your notice. So while doing this, creating this windows of size 4, let's say from 4, 5, 6, 7, we predicted 8. And then from 5, 6, 7, 8, we predicted 9. Similarly, using 6, 7, 8, 9, we have predicted 10. Now, because we are having one more window, that is 7, 8, 9, 10, we are still having this window of 7, 8, 9, 10. So this window is going to predict the value in the future. Now that value, we don't have any respective value in the validation data. And that's why we cannot compare that last value that our RNN forecaster will be generating. We will not be able to compare it with this validation data set. So the basic idea over here is, after passing this whole data set into that RNN forecaster, it's going to give me the whole prediction based on this data. And now what are the values that I'll be using in order to compare it with this validation data set? I'll be taking only the values which is with respect to the validation data. So for that, I'll be skipping the last value. And then after skipping that last value, whatever is the length of my validation data, I'm just going to take that part out of that whole RNN forecaster. So in order to explain this in a much more better way, I'll just now zoom out and come to this particular step. And over here, we can see that after creating the RNN forecaster, I'm taking specific values. So this is much more complicated. So what I should do instead of this is, see, even this is correct, there's nothing wrong with that, but a easier explanation to this is, because I know that my inside this validation data I am having the length of 327, because if I just scroll upwards, there was a line that we had written somewhere that the validation is containing the size of 327 values. So where is it? Let me, yeah, over here. uh, After creating the train test bit, yes, 327 is the validation data sets. So see, now what I want to do, as I've explained over here, that the values that I'm going to compare with the validation data set are nothing but skipping the last value from the forecasted results. I'm going to take the last length of that validation data that I'll be having. I'll just grab that and simply go ahead and compare it with the validation data. So instead of writing this, what I could have also written is, I'll just write it as a comment over here, which you can also try. It will give exactly the same result. So RNN forecast, and inside that what I'm doing is I'm going to grab my minus, like the last 328 values. In order to grab this last 328 values, I'm just going to use the negative indexing, that is my minus 328, the data that is my last minus 328 data, and then just consider the next value still the last value, but I'm not going to include that last value, and that's why I'm just saying that till last value I want to take the values. So this is what is going to contain the last data set in last 327 data points after excluding the last value. And then I'm also having this comma 0. So because we know that we are having a column matrix over here, that's the result we'll be getting in the format of column matrix. We are just converting it into the normal row kind of data, one dimensional data, which will be used in order to plot. And that's the reason that I'm using this comma 0 over here. So if you want to understand what is happening over here is, see, first of all, you need to know that what is the split time. Split time is nothing but the index where I'm doing the split on the original data in order to get my train and validation data set. So just because I want to help you understand this with the help of this example, let's say that over here on that particular value, we are having this value of split time. So all the values till this 7, I'm going to take it as a training data, and after that values I'm going to consider it as a validation data. So what I am doing is I'm doing the RNN forecast, and I'm going to that particular index, and then I'm doing this minus window size. The minus window size, because in this case was 4, so I'm going 4 units back. So from 7, if I go 4 units back, that's my 1, 2, 3, 4. So now I'm going to go to that particular point and then use this inputs, and then whatever is the next value, that value is what will be compared with that validation data set. So that's exactly what is happening over here. But now, just if it's confusing you, the basic idea that as I just explained, what we are doing is we are just considering the minus or the last 328 data set, and then just removing the last data set. So we are having total of 327 data points, because the last value is nothing but the future value, which respective value in the validation data we are not having, so we cannot use that to compare it with the validation data. So the 327 values are the values after skipping that last value. The remaining values from the end till the 327 will be the one which I am going to pick it out from the RNN forecaster, and then I'm simply going to use it and plot it over here. And that's the kind of fit that we have got, that the blue line that we are seeing behind is the original validation data on which we are having this predicted values, and we can see that it is working pretty much good. And yeah, that's the kind of the output that we have got. This is pretty much satisfactory output, that I would say, in my opinion, because this is a real world time series. So yes, this is the kind of result which we have achieved with the help of the parameters that we had defined. Obviously you can play around with the parameters and even get much more results, much more better results. You can just say that this original peak was over here, but the peak that we got was over here. So you can try to see if we can get some extra values over here, right, after doing the manipulations of the outliers and the stuff that we have discussed earlier. So after doing all these kind of changes, doing the hyperparameter tuning, see if you are able to get much more better fit of the predicted data on the validation data. So after creating that final forecasting results, now I want to compare it with the validation data and compute the mean absolute error. So what I'm doing is I'm using tf.keras.matrix, and then I'm just using MA, that is the mean absolute error, and then just passing in the validation values and that forecasted values, and then dot numpy is just going to convert it into the final value, and that's what I'm using. The final MA value on the validation data is 13.122. So now according to my opinion, this is pretty much decent MA that we have achieved on the real time series data. So yes, this was all about this particular project, where we have started by looking at what was the kind of data, then understood how to create windows for LSTM to understand data from it, and then we have just learned how our model is going to go ahead and predict the next values with the help of this window data set. So now, what are some kind of tasks for you for this particular project? So as I already mentioned, that using the disk plot and the box plot that we had created earlier over here, you are going to see, based on this, what are the conclusions that you can make and how can you get rid of this kind of outliers, or maybe manipulate in a way that you can get better results. So that's what you're going to do in this first task. Then the next task is to implement other callbacks apart from the learning rate scheduler in order to train your model efficiently. You can monitor your model much more efficiently than what we have done over here by using the other callbacks that we had used in the previous project. And you can find that notebook over here by clicking over here. You will be just redirected to that GitHub page where we have uploaded that particular notebook. So you can just click on this SDSI. This is the thing that I was talking about. And yeah, after clicking on this, you will be getting the whole notebook, where you can just go ahead and cross check what are the callbacks that we have used and simply try to see if you can use them over here and monitor your training much more efficiently than what we have done. So that's one of the tasks that we'll be doing. And the third task is to add a piece of code to this notebook to predict some of the future values from that last data points. So if you had noticed over here, we had created one value of the future. Now like that, if I ask you to predict some more values in the future, how will you do it? Try to figure out that logic over here. How will you manipulate that forecasting function, or maybe create a new function that will be helpful in order to create future values? And then once you are having that idea, you start figuring out how to predict the next values, and then just predict the whole solar cycle 25. Like currently we are in the solar cycle 25, right? So see how this number of sunspots, the mean number of sunspots on monthly basis are going to change. So that's the third task that you are going to do. And in the fourth task, you are going to create your own function that will take in that one-dimensional data and convert it into the shape that is required for the LSTM. To convert it into three-dimensional data, the first value will be the batch size, the next value will be the window size, and the last one will be the number of features. And because it's a one-dimensional data, that value will always be 1. So you can use for loop or any kind of other techniques apart from this TensorFlow method in order to create your own function that will create this kind of windows. So these are pretty much the tasks that we'll be doing. And if you are able to accomplish this task in whatever way that you are going to do, we are going to go through it. Our team is going to just evaluate what you have done. And you are going to get this chance of earning the certificate if you're going to complete all these tasks. So make sure that you are going to complete it properly and submit your notebook by using this form. If you are going to click this form over here, it will redirect you where you'll be able to fill in the informations of the project ID and the project name, which you can find as always at the start of this notebook. If I just keep on scrolling, you will be getting it. Yes, over here you can get the project ID and the project name. Just make sure that to copy it properly and paste it over here, because this project ID and project name should be pretty much correct. If it's not correct, you will not be able to get yourself marked properly. And then you just keep on writing all this kind of other information and submit the final solution notebook. And that's all pretty much about it. And just make sure that if you have not already created your account on this Spartificial's website, you just click on this link and first of all go ahead and sign up yourself over here with the help of maybe the Google account, or you can directly go ahead and create your account over here. Once you are done creating your account on this website, you come over here and just submit the form. And if you have just enjoyed how we have done the projects over here, just make sure to support us, show us some support with dropping likes, comments on some things that you were able to learn. If it was helpful for you or not, it will really keep on motivating us to create this kind of content for you in the future. So yes, thank you for watching this video, and I'll be again back with some exciting projects like this, and see you in the next one. If sunspots are highly active, more and more solar flares will create an increase in geomagnetic storm activity for Earth. Therefore, during sunspot maximums, the Earth will witness an increase in beautiful northern and southern lights and a possible disruption in radio transmissions and power grids. The storms can even change the polarity in the satellites, which can eventually damage the sophisticated electronics. Therefore, Oftentimes, scientists will pre-position the satellites to a different orientation to protect them from the increase in the solar radiation when a strong solar flare has occurred. And not only this, it can also disrupt the biological DNA of our astronauts. And therefore, it becomes very much crucial for us to predict based on the sunspots how solar flares are going to travel towards us and save our technology and astronauts out in space.